Welcome to our exploration of computing's first spark, a compact lecture tracing the origins of modern computing and why these early breakthroughs still matter. Over the next slides, we'll follow key inventions and ideas that turned counting machines into programmable systems, setting the stage for the technology that powers our world today. This slide shows how punch cards shaped early data storage and processing, starting with Hollerith's 1890 census tabulator and moving to IBM's 80-column card in 1928. These physical cards became the medium that fed the first electronic machines, seeding the software era and giving governments and businesses a practical way to handle large datasets efficiently. The Atanasoff Berry computer in 1942 introduced several techniques that mattered: vacuum tubes for binary operations, regenerative memory, and early ideas of parallel processing. The diagram here highlights how those components combined to demonstrate that electronic elements could outperform mechanical relays, an important proof of concept that helped clear the path toward ENIAC and later electronic designs. ENIAC, built by Mauchly and Eckert in 1943-44, showed the world how quickly calculations could be done using electronic switching, programmed with switches and cables to reach thousands of operations per second. The public demo in 1946 convinced audiences that complex numerical work could be completed in seconds, not hours, changing expectations about what machines could deliver. The 1945 EDVAC report formalized what we now call the von Neumann architecture, a single memory storing both data and instructions, and a sequential fetch-decode-execute cycle-driving processing. The diagram links that model to today's microprocessors, showing how a small set of architectural ideas, memory, an ALU, and step-by-step execution still underpins modern chip design. In 1948, Manchester's Baby validated the stored program concept by running a 17-instruction program from CRT memory, separating software from physical wiring. This slide emphasizes how software independence transformed machines from fixed-purpose devices to flexible platforms, marking the moment programming moved from rewiring hardware to manipulating stored instructions inside memory. UNIVAC. I catalyzed corporate computing by bringing large-scale electronic machines into government and business use, notably the U.S. Census Bureau in 1951 and commercial payroll and inventory tasks at GE. The photo and notes highlight how proving real business value sparked corporate demand, showing computers could produce measurable economic returns and accelerating broader adoption. The 1964 IBM System 360 launch represents a paradigm shift toward compatibility and scalability, unifying small, medium, and super systems on one platform so the same code could run across sizes. That strategic compatibility locked in massive software investment, helped customers scale without rewriting code, and propelled IBM to dominant market share in the mainframe era. Each historical milestone here functions as a micro-lesson. The ABC showed electronic binary logic, Manchester's Baby proved stored programs, and the 360 taught modular scaling and platform compatibility. Together, they demonstrate how incremental innovations accumulate, teaching us that small, focused breakthroughs can compound into sweeping, revolutionary change across the industry. This slide outlines a microlearning framework for understanding computing's evolution. Start with concise facts, move to immediate application, space learning over time, and aim for durable understanding. Revisiting brief pivotal episodes, each illustrated here, reinforces retention and builds the layered knowledge needed to grasp complex technical histories and their modern implications. The foundational concepts from computing's birth continue to transcend changing hardware. Vacuum tube speed and stored program flexibility gave rise to scalable, compatible families of systems, and those ideas persist in modern chips, cloud racks, and AI accelerators. The point here is that core architectural principles outlast specific technologies and keep shaping new generations of systems. Finally, by By tracing origin stories, we equip learners to recognize and shape future paradigms like quantum and neuromorphic computing. Understanding how past micro-breakthroughs changed the trajectory of computing helps learners spot emerging patterns and even craft the next small innovations that could redefine computing's future, turning historical insight into forward-looking action.